All right, welcome. So in this video, I want to talk about Turing completeness, an idea that we mentioned in the last video, and then also extend that to this idea that we call the Church-Turing Thesis. So to begin, I'm just going to add an extension, something we haven't really been focusing in this series of videos. We've been computing languages, or we've been computing membership in languages. I called it sort of the language membership problem. One of the valuable things about the language membership problem is that it has a Boolean output. That means its answers are just yes or no, and that makes things a little bit simpler to analyze some of the computation that we've been studying. But another area, especially where computation began, or the study of computation began, was the study of computing mathematical functions. And Turing machines can also compute mathematical functions. What do we mean by mathematical functions? I mean by like n squared or x plus y. Things like these are mathematical functions that take inputs and produce outputs. And so far, our output has just been accept, reject, but we might want to make a more sophisticated definition of a Turing machine that also can output numbers. So the way we're going to do that is by just considering the output of the machine to be whatever happens to be written on the machine when we halt. And in these type of machines, we typically don't have accept rejects. We might, depending on how we're defining things, but more commonly what we just have is a halting state that says, okay, I'm done computing, and then whatever we might call it the output state. Now when we get to it, we just read the tape and that's our output. So another thing that we're going to need if we want to compute mathematical functions is we're going to have to encode numbers in some way, because numbers, we're working, technically our Turing machine and our language membership problem are defined in terms of strings. We've been talking about strings, not numbers. And we can, of course, encode numbers as strings, but we do that using some base. For simplicity, we've been using unary, okay? And these represent the numbers 0, 1, 2, 3 by using, say, the empty string to represent 0, 1 0 to represent 1, 2 zeros to represent 2, and so on, okay? There are many ways we could represent numbers, of course. For instance, another way we can represent numbers as strings is with Roman numerals. Probably not a great way, but you can imagine making a Turing machine that computed with Roman numerals. That sounds painful, and I please don't do that. That's why we don't use Roman numerals, of course, right? That's why we use the Arabic numerals. And so we might want to use more than just the 0. We could use 0 and 1, and that creates binary. And in fact, that's our default, just because it's a little bit simpler when we're working with Turing machines, but also with computers, is we use the binary number system. And so here we're using, we've encoded the numbers as binary strings, just like we have down below. We've encoded numbers as decimal strings, or we could write them in octal or hexadecimal or something else, on any other base we'd like. But we need to sort of recognize here that these technically are encodings now, that the strings that we write of numerals here encode conceptually numbers. Numbers are a conceptual thing, an abstract thing that we represent physically by these symbols. Now we are going to talk about other types of encoding schemes in our next video, but for now, let's just stick with our encoding numbers in some kind of base, and binary is going to be our default base. So what that allows us to do now is define what it means to compute a function for a Turing machine. And in fact, we give this a name. We say a function is Turing computable if and only if there is a Turing machine that halts on every input, and when it has an input that encodes a number n, it halts with f of n written on the tape. So again, we're using some encoding. Binary is our default here. Of course, we could do it in unary too, where we take the number that's written on the screen, we transform it into f of n. Okay, so I want the title of this talk is the Church-Turing Thesis. So whose Church, Alonzo Church, is the other part of this. he was an American mathematician and a contemporary of Alan Turing. That means he did his practice around the same time as Alan Turing, and they were both interested in the same thing, which is computability and computing functions. So he created a different model of computation independently of Turing, trying to answer these same types of questions: what can be computed and what cannot be. And his is famously known as the lambda calculus. And if you've ever used lambda functions in any of your programming languages, they've found their way into all kinds of programming languages. They have been named, lambda functions are named after the lambda calculus invented by Alonzo Church. So lambda functions in most languages are also known as anonymous functions usually. And what makes them anonymous is an anonymously defined function is a function without a name. So we might make a mathematical function here, f of n equals n squared. Well, here's sort of an anonymous function, at least written kind of in the formula that the lambda calculus uses. We have a function that takes an input n, it's got no name, and it maps itself to n squared, at least this function that I'm using as an example. So in the lambda calculus, there's sort of this notation, and we're not going to go into too much detail about it, although it would be certainly interesting to learn more about the lambda calculus if you're interested. In this case, we've got that function we've defined, and we're now calling it. So this is like saying f of 5. If we had named this f, but since it had no name, we just used the function as its own name, and we use it to call, we call it on this argument 5. It maps its n to n squared, so the answer to this would be 25. Very straightforward. In the lambda calculus, this is part of where things get interesting, anonymous functions can be applied to other anonymous functions. So we can take this function we've been working with and apply it to this other function that maps m to m plus 1. And then that would give us something that maps m to m plus 1 squared. So we can compose functions together and build new functions. Church was interested, as was Turing and others at this time, in what are the kinds of functions that you could compute when you had a very simple definition of computation like this. So he started with this idea of the lambda calculus, but then he also wanted to only start with the very simplest set of definitions that he could come up with. So here are some that we could begin our definition with. His is slightly different than this, but this is a simple exploration. We can imagine saying, okay, we need 0. We need something to get started with, so I'm just gonna say we're gonna make a definition 0 is 0, 0 is just a thing. But we can now define these other symbols, 1, to be just this function. So, sorry, we don't just need 0, we need this function as well. What's this function? This is the increment function. This is like plus plus, right, in our Java or C, right, C++. We're taking some function and we're just incrementing it. So we input n, it outputs the output. So if we had 0, we could define 1 to be just take this increment function and apply it to 0. That gives us 1. Then what's 2? 2 is just apply the increment function to 1. We now have 2. We can now define the whole natural numbers. So what was interesting to Church, but also to other mathematicians at this time, was recognizing that the whole set of natural numbers, there are infinite of them, can be defined by just recursively applying these two definitions infinite times, which is really interesting. And this kind of pattern of defining the natural numbers was repeated in set theory and other formal models as well. Okay, so this is one way to define the natural numbers, but what was interesting to Church was that within this very simple setup that he had started with the lambda calculus and just these two definitions, now he had the natural numbers to work with. On top of which, he also had a number of other interesting functions that emerged out. That we had the increment function, but we also had the increment by 2 function and the increment by 3 function that emerged out by just nesting these functions. So let me maybe go through this here. We said that 1 was just the increment function applied to 0, and 2 was the increment function applied to 1. Well, let's unwrap that a little bit. The 1 was just the increment function applied to 0, so I applied that here again. Now, the way we did it in our original definition is we said take this and apply it to here, and that will give us 1, and then take this and apply it to the 1, and that will give us 2. But now let's do it the other way, and let's take this function and apply it to this function. What does it give us? It would give us this function, n goes to n plus 2. And then if we did it 3 times, if we compose the increment function with itself 3 times, we get increment by 3, and so on. So we can get infinite new functions in this way as well. So now we're noticing, oh wait, with those 2 simple definitions, we've got infinite numbers now, we've got infinite cool addition functions, and we can define other functions. We can start defining other functions from this set. Here's another one that, this is a function that returns a function. And if we call this function with just a single argument, 5, it gives us back a function. And so if we call it with 2 arguments, a 5 and a 4, it actually will then return us back to a number, in this case, the number 9. And we can use this to define a shorthand for functions that take more than 1 argument. And again, with this idea, Church sort of ran with this idea and said, okay, what are all the functions that we can define? We can get addition, we can get multiplication, and went on to show that there's this whole set of mathematical functions he called the computable functions that can be defined using the lambda calculus, or can be computed rather, learn with the lambda calculus. And so this set of mathematical functions he called the computable functions. There's a third set, because the computable functions that Church had come up with his lambda calculus were a set of functions that were independently defined from Turing computable functions. So we've got the Turing computable functions, we've got the computable functions that with the lambda calculus, and then we have this third set called the general recursive functions that were studied by Kurt Gödel, who is known famously for the incompleteness theorem, a very interesting theorem that has lots of parallels to the topics that we are talking about right now. So if you're interested, it has to do with the incompleteness of logical systems, very interesting. And another mathematician, Jacques Herbrand, they came together and defined this third set of functions called general recursive functions using recursion, composition like we were just looking at, and minimization. This third set of functions, now these mathematicians all got together and they said, we have 3 different ways of defining what is a computable function. And we kind of want to know which one is the best way. One of these sets of functions is likely to be the biggest. And so one of us has come upon something that's the coolest, and the rest of us probably have things that should go by the wayside. Turns out that was not what happened. Instead, what happened is they found that all 3 classes were the same. That this was proved by Turing and Church, as well as Kleene, who was, we saw him earlier, the Kleene star is named after him. These 3 classes were all proven to be exactly the same, or put another way, that these 3 models of computation, the lambda calculus, the general recursive functions, and the Turing machine and Turing computable functions, are all equivalent in terms of their power for computing mathematical functions. And we can do this for languages as well. So this realization was certainly cool and interesting. As researchers, they did not expect necessarily that their models would be equivalent in power. They may have had, I wasn't around at this time. They may have had some suspicion, of course. They may have thought that that was a possibility, but they may have when they realized that all 3 classes were the same, that led Church and Turing to come up with a hypothesis. And that's what we call the Church-Turing Thesis, or the Church-Turing hypothesis, that any physically realizable model of computation must be computationally equivalent to the Turing machine, or be less powerful. That's something that's not, I didn't put on my slide here, but it's also a possibility. We've seen lots of models, so far in this series of videos, like finite automata and context-free grammars, that are less powerful than a Turing machine. But anything you can come up with is going to be either less powerful than a Turing machine, or at maximum equivalent in power to a Turing machine. Now this is stated as a hypothesis, not as a theorem. Almost everything we've been looking at so far in this series of videos has been theorems. This is a theorem. Proven. We've proven it. A hypothesis, of course, is what a theorem is before it's proven. It's a guess. It's what we think might be true. And it remains a hypothesis or a thesis until, sometimes also called a conjecture, until it is proven. And this one has not been proven. And unfortunately, this particular one is likely unprovable because the way that it is stated is just too informal. Because we're saying any physically realizable model of computation. What does that even mean? That's kind of hand wavy. We haven't really said, what does that mean? What we're trying to capture is the idea of any machine you could build to compute. But the rules of what a machine could look like are not stated. So there's the possibility that there are physical powers in the universe that we have not uncovered yet that could be more powerful than a Turing machine. Indeed, that is what the quantum computer posed as a tantalizing possibility. When we started unlocking the ability of using quantum mechanics to do computation, there was this tantalizing thought that maybe we've discovered some physical property of the universe that is more powerful than classical computing. Turned out the answer was no. So that was the first time that, or one of the first times, maybe the first real important challenge to the Church-Turing thesis that emerged, that indeed confirmed the thesis. And of course, every time we get a physical realizable model and we test it and it turns out to be equivalent to a Turing machine, that helps confirm the thesis, but no single one confirmation is going to confirm this thesis. Nothing. We can't prove this thesis just by enumerating lots and lots of models and saying they're equivalent. We have to prove this by showing every model is equivalent, and that's either going to need some new kind of math that we haven't, figured out yet, or it's unprovable. And so that's why this remains a hypothesis, a thesis, a conjecture, and not a proven theorem. Now, with that said, it's going to be hard to find a computer scientist out there that does not believe that this is true. So even though it is a thesis or a hypothesis, there are many of us that believe that this is true, that there are probably not magical properties in the universe that we have not already uncovered that can be used to do more interesting computation than a Turing machine. Okay, so with that said, we have tested it with more formal models over the years. Often these formal models have not been created as a means to test this thesis. They've often been created for other reasons, but then have been swept up into this because someone says, hey, maybe that's Turing complete, and then they are studied. So there are a couple cases that I want to bring up. I've already mentioned the lambda calculus and primitive recursion. Another one is the game of life. I have a video on the game of life in my series on complex systems, so please check that one out. The game of life is a complex system. It's a cellular automata where the state of the automata evolves or changes from a set of simple rules explicitly from the last state. So a current state always completely dictates the next state. It turns out that this game of life is Turing complete. It's not just Turing complete, but you can build a modern computer inside the game of life. You can also build the game of life inside the game of life, which is kind of cool. It's got this recursive structure, so you can build a simulation of itself inside of itself, which is really interesting. And someone has shown that you can simulate a Turing machine with Kanye's game of life. A somewhat simpler cellular automata, because it's one-dimensional instead of two-dimensional, this is a two-dimensional one, comes from Stephen Wolfram, known for Wolfram Alpha. You may have used that for your math homework. Wolfram is a scientist and a technologist and an entrepreneur who, of course, created Wolfram Alpha, but he also published a very interesting book where he studied cellular automata in the late 90s or early 2000s called A New Kind of Science. Very interesting book to read, but one of the things he talks about in that book is a rule 110, which is also, he proved to be Turing complete. So another interesting cellular automata, he had no intention of showing it was Turing complete. Originally, that was not the goal, but it did turn out to be Turing complete after analysis. There are also practical computing devices that are Turing complete. The von Neumann computer architecture is Turing complete. What is the von Neumann computer architecture? That's the architecture that we currently use for all of our computers. So that is this CPU, the central processing unit, plus some memory, plus a bus that moves memory into the central processing unit. You can think of this as kind of being the tape, right? The memory is where the tape is, and the central processing unit kind of being the state machine. And so all of that has been shown to be, can simulate a Turing machine, so it's Turing complete, and vice versa. The one sort of asterisk that I will put on that is that technically our modern computing systems do not have infinite memory, which a Turing machine does. And so for that reason, there's this very technical, we could say they're really finite automata with just lots and lots and lots of states, like trillions of trillions of trillions of states. But that is not super useful for us. We just instead say, okay, we think of it as a model of a Turing machine, because if you were running out of memory, you can just put more memory in, up to the point where you have enough memory to do whatever it was that you were trying to do. With that asterisk, then the von Neumann computer architecture is Turing complete. That's why we can use Turing machines as a model of our modern computing and information technology. All of our programming languages, all the general purpose ones that is, Python, Java, C++ languages, JavaScript, any of the other ones that you might use, Rust, for instance, whatever ones, niche ones that you might think of, all of them are Turing complete on purpose. That's the point of them, is to allow you to do whatever you could do on a computer, so that's their goal. But also many specialized programming languages where the goal is not to be general purpose and be Turing complete. Many of them also are Turing complete by accident, maybe. So an example might be Excel or SQL or LaTeX or text for typesetting documents. With that said, maybe HTML might be in there too. I didn't notice it on my list, so I didn't add it. But these are things that are not intended to be Turing complete, but maybe turn out to be because of what we build into them. And finally, you can find a list of some really interesting and cool models that are definitely unintentionally or accidentally Turing complete. Minesweeper, if you give it an infinite grid, is technically Turing complete. You can set up a sequence of mines as the input, and you can say that processing that is like computing. Again, who came up with that? Who proved that? Well, at some point, there became a small little cottage industry of Turing complete proofs that were for master students and grad students who were interested in doing a project, and they would come up with something. They say, hey, I think Minesweeper might be Turing complete, and then they would go prove that for their master's thesis. Minecraft is another one. Magic the Gathering has been shown to be Turing complete. Okay, Minecraft, actually you can build computers in it, so you have the crystal magic, I can't remember how it works, but you can build computers in there. Magic the Gathering has all these different states, so there are specific cards that you can load up, I think, with counters that if you set up the right sequence, you can basically use them as memory, like stacks and so on. So they're a very interesting way to use Magic the Gathering to show that it's Turing complete. And then the fun simulation game Dwarf Fortress, which has been around for 30 or 40 years, highly detailed, maybe an inspiration for games like Minecraft and some of these other open world games. Dwarf Fortress has also been shown to be Turing complete. Again, if you're interested in finding a whole bunch of funny, silly things that have been proven to be Turing complete, go jump over to the Wikipedia article on Turing completeness, and you'll probably find a nice list there. And you can probably, jump down the rabbit hole from there to find other articles about interesting things that have been proven to Turing complete. So this has been a fun video on the idea of Turing completeness and the Church-Turing thesis. I hope you've enjoyed the video. We'll see you in that next video.